do, do, do. Hopefully, we're live. Are we good? Um, looks it. Okay, so um, today this stream, we're gonna go back onto A-level maths. The last few days, it's been a GCSE because obviously there's a GCSE exam this earlier this week on Thursday, but now we're gonna jump back onto A-level maths. And we haven't done a lot of it actually, but I think the first A-level maths exam's in June, if I'm right. So yeah, we're doing some more stuff in the lead up to that. But yeah, today we're going to look at another past paper. Now, yeah, last time we did June 2018 paper one, we finished that. So now I guess it makes most sense to do paper two. And yeah, that's what we're going to look at the pure bit. So in the run up to the first pure exam, um, we'll be looking at some past papers. We're going to have some topics and stuff like that. So yeah, that's the aim for today. Is to look at another paper, past paper, and yeah, I'm going to leave that there. Actually, I'm going to stop the waffle and just jump right in because obviously A level takes longer than GCSE, so I want to make sure I have enough time to do most of it. So yeah, let's jump right in. Okay, question one. So I have a function here, and first of all, what's to find GG of 5? Now, very similar question to what you can get GCSE actually, a GCSE question this is. And the thing you need to bear in mind is that this is saying G of G of 5, okay? It's a composition, it's a composite function. We are substituting G of 5 back into G. Okay, this is what this is saying. It's not times in the functions. And you can see this because there's no brackets here after the first G. They're hidden. So if you put a bracket here, that's what this is saying, okay? Just to clear that up, but hopefully you should recognise that. So yeah, so that's what we're going to do. So G of G of 5. Well, that's G of 5 first of all. That might help. G of 5. Well, that's going to be two sub 5 into x. So 2 of 5 plus 5 over 5 minus 3. Simplify that. 2 times 5 is 10 and 15. 5 is 15. 5 minus 3 is 2, and that's it. So therefore, G of G of 5 is now simply G of 5 over 15 over 2. Now you can again substitute that back in. So 2 of 15 over 2 plus 5 over 15 over 2 minus 3. And you can just bung that into a calculator, okay? And actually, let me get my calculator, pull it in. Um, do, do, do. So 2 lots of, well, that would just be 15, wouldn't it? 15 plus 5 over 15 over 2 minus 3 should get you 40 over 9, apparently. Cool. So that's part A. Quite a nice intro to the paper. First question. Part B says state the range of G. Okay. Um. Not the nicest question. Uh. Well, I guess use this as type. So this is the initial value for x we can have, right? X is 5. So I guess with this, the idea is to try certain values of x and see where the like function tends to, right? So let's just plug some values in. So g of 5, which is the minimum. Well, we had to work out g of 5 in our part A, right? So that's 15 over 2. And what happens if we pick now? Let's consider very large values of x. So again, if you're not unsure about this, how this function behaves, because it's not the nicest to be fair. It's not simply just a reciprocal. It's not like that because there's two lots of x, so it's a tad bit more complicated than that. Anyway, so um, let's try uh, a million. Okay, 2 over a million plus 5 over a million minus 3. Uh, an interesting way, that gets you it gets you 2.00 something 11. Now, actually, this is actually kind of suggesting, um, as you get closer to infinity, the function tends to 2, right? That's what seems to be what's going on here. And actually, this is true, because with fractions like this, but they don't show you this sort of thing in the A-level spec, but it's weirdly something they expect you to know, but they don't explicitly teach it. So if you look at this g of x, it's divide both sides by x, so that you'd get this is equivalent to 2 plus 5 over x over 1 divided by x minus 3 over x. These are equivalent if you just divide 3 by x on both sides. Okay, I'll get lost. Yes. Well, actually, when x is big, 1 over x will go to 0, right? Think about it. If you divide by an absolutely massive number, so x infinity, that will go to 0. Check that with your calculator. Plug some very big numbers in. And you can kind of see that with the reciprocal graph as well, right? So this is the reciprocal graph. And then when x goes to 0, no, when x goes infinity, the graph goes to 0, right? Y is 0. So actually, yeah, we can basically substitute the 0 in. So then we can say 2 plus 0 over 1 minus 0. And this is when x is infinite. So when x is big, this goes to 0, this fractional bit, okay? So when x goes to infinity, this fraction goes to 2 over 1, which is 2, which makes a lot of sense with what we're getting here. As we pick larger and larger values for x, this goes to 2. So actually, yeah, so actually goes to 2. So our starting value at the range is 15 over 2. And at the end, when x gets big, it goes to 2. Now, 15 over 2 is bigger than 2. So what this is suggesting um, is this. Okay. So initially, remember it said x is greater than or equal to 5. So x is 5 is the minimum value of the function here, the minimum domain of the function. And that gives us this, and it goes down to 2. Because actually it's continuous as long as x is 5 or above. There is a discontinuity when x is 3. Discontinuity obviously just meaning whatever this graph looks like, there's like a little gap at 3. This is not what the graph would look like, but there's like a little gap at 3. And continuous just means the graph you can draw without moving your pen off the paper, right? There's no like jumps or anything like that. So when x is 5, the function will just keep going. There'd be no jumps, so there shouldn't be so there shouldn't be able to jump away from this interval here. And that's only for 1 mark. So it's not the most rigorous explanation, to be fair. But it's a tricky function. That's a very nasty question, I'd say. I think that's one of the hardest questions in the paper. If I'm a big, I've never even seen the paper, but I could already tell. It's not a nice function of giving you this to ask the range of. Also, bear in mind the range is y here, so g of x, the whole fraction, not just x. The main is the values of x. The range is what the outputs are, which is this whole fraction here. Okay. Okay. There are more precise ways to prove the range, but that will involve differentiating, considering turning points, so maximum and minimum, considering continuities, and obviously second derivatives to consider the nature of maximum and minimum. But it's 1 mark. they weren't expected to do that, so you just need to consider the behaviour as x is at the end point. So the starting point of x is 5, and I guess the end point, although it's not a definitive value, would be infinity. So it's asking you basically what happens at the beginning and the end for 1 mark, right? They're not expecting a lot of reasoning there. Uh, so yeah, and I guess the last point to note is that it's equal to 15/2, but not equal to 2 because 2 happens. Well, it can't happen. 2, I guess, happens in a way when x is equal to infinity, but a number cannot be infinity. It's tending to 2. It would never be exactly 2. Okay. Hang on, I'll be back in a sec. Apologies. Okay, I'm back. I do apologise. So yeah, so we were talking about the range of G. Hmm. So yeah, I guess to recap, um, I looked at the starting value, what happens at the start of the domain, which is 5. I plugged that in. Well, we worked out in part A. G of 5 is 15 over 2. And then if we look at the large values for x, when x goes to infinity, we saw that it goes to 2. And actually, we've verified it here. So if we know that 1 over x goes to 0 as x, x goes to infinity, which hopefully you do realise that this is true, then actually we can manipulate this a bit by dividing by x on both sides. And you see here we have over x, which will go to 0. So actually the end behaviour, the long-term behaviour is x goes to infinity, is g goes to 2. Um, so yeah. And yeah, that's the whole idea with functions, I guess, is to consider the behaviour at the endpoints. And if there's any maximum or minimum, if it's increasing or decreasing. But if it's only one mark, they don't expect you to differentiate by turning points and all that sort of stuff. Um, um, and yeah, and of course the function will be decreasing, wouldn't it? Because as you get larger and larger values of x, the numerator will always be bigger than the denominator, and the numerator will always keep getting bigger because we're adding 5 and we're minusing 3, so the denominator will always be smaller than the numerator for like small values of x, right? But actually, when x is bigger, the 2x will be far bigger than x. If you double a big number, that's far bigger than the number itself. So the numerator, hopefully you see here by inspection, will always be bigger than the denominator. So it will always be, at least when x is above 5 anyway. So it will be a decreasing function. So as you get higher and higher values for x, and you can try to test with the different values of x, the function will get smaller and smaller. So actually, oh, and this is the wrong way around as well. It's the minimum value is 2, but of course it can't actually be 2 because that's when x is infinity. But obviously, x only tends to infinity. You can't have a number be infinity. That's not a thing. But it tends to infinity, meaning it will tend to 2, but never be exactly 2. But actually, the starting value is 15 over 2 when x is 5. And then it decreases from there. So the upper limit, so the highest value will be 15 over 2, and then it will tend to 2. So hopefully you realise that. So that's the idea with functions, right? Is to consider the boundary. So I guess like the minimum, the maximum. So here it's between x is between 5 and infinity. So you look at what happens at the minimum and the maximum values of x. And you also then look at if the function's increasing or decreasing in between to see if it spikes up. So for example, if it's spiked up, so the maximum here would be here, not the endpoint. Uh, or if there isn't, if it's increasing or decreasing. But here it's, as I said, it's decreasing because the numerator will always be bigger than the denominator, and it will keep the numerator will always keep increasing, so that the overall fraction will be. Hang on, I've not reasoned that well, have I? Actually, um, no, I don't think I've explained that very well. I do apologise, but it's decreasing. There's a way you can verify that. Again, if you differentiate it and obviously find turning points, you won't find any. Uh, You won't find any minimums and the max or maximums. Well, in this range anyway. Well, anyway, the whole idea is it's one mark, so you can kind of reason. Well, you won't expect you to differentiate by turning points, so that will you just consider the endpoints. I know I do apologise if it's spelled very well. I've just been a bit rushed. Something's going on. Uh, but I probably will. I know a lot of people struggle with range and stuff like that of functions the most. It is a very tricky, and I don't think this spec explains it very well. If I'm honest, there are various techniques you can do to study the range of a function and the domain of it. I might do a video on it, perhaps on the topic at a better time. But that's sort of the process I'm thinking of, right? So it's not the most rigid way, granted, but it's only a mark. So you just could, I guess, consider up the endpoint behaviors, and then it clearly must be decreasing. I'll come up with a better explanation for why it's decreasing, other than just saying differentiate by turning points. You know what I mean? If there are any. But yeah, I guess the function will look something like this. It's kind of like a reciprocal graph, I guess, in a similar sort of way. So it follows the same sort of behavior, I guess, as a reciprocal graph, so like 1 over x. But yeah, anyway, I'll leave it there for now. But yeah, that is the answer. So that anyway, I will go back to that at a later date. But that's just, I don't know, the answer. Yeah, I guess if you're struggling, it's only a mark. Okay, that's out the way. I know that wasn't the best explain. I do apologise. It's a bit rusty, a bit rushed. I apologise. But that's the answer, and that's how I kind of think about it. But anyway, part C then says find g of inverse. So okay, we're back in a comfortable domain. No pun intended. G inverse. Well, even from GCSE, you should know how to invert a function. So again, the essentially with inverting a function, the x and y's switch places, and that is because, as you should also know, for a general function, I don't know, like that, f of x, if you invert it, you're essentially geometrically reflecting it in y equals x. Okay, and so actually, when you do reflect it in that way, uh, the x and y switch places. Okay, it's kind of like, say if you have this point on say if you had this point on f of x. Say if you had the point here, if we reflect it, it would go onto here. And obviously, hopefully, you can easily visualize here the x and y switch places because it's on the x-axis, but now it's on the y-axis. That would be the inverted point, and that is all that inverted function is doing, which is why the method for this to invert a function is to say, well, y is g of x. So what's g of x then? Let's substitute it back in. So g of x is 2x plus 5 over x minus 3. Cool. And basically, because like I said, they switch roles, but that's what we're going to do. We want to get all x in terms of y, and then flip it the other way around. So we want to make x in terms of y here, so x on its own. Well, there's a lot of x's here, and there's a fraction, so the best thing would be rearranging, again, just times across. So I did do this on my GCSE, one of my GCSE videos, actually. So it's quite a GCSE-esque topic, actually, so hopefully it should be quite comfortable. But anyway, let's go through it. So to get x on its own, let's get rid of the fraction, times by denominator. So you get this, expand it. Cool. Let's group the x's on the one side. So xy minus 2x is 3y plus 5. And then x of y minus 2 is 3y plus 5. And x is 3y plus 5 over y minus 2. Cool. And then, like I said, they switch places. So the inverse then is simply you put the x's here instead. So g inverse of x is 3x plus 5 over x minus 2. Cool. And pay attention, it says stay in its domain. Now you should know that that again, because they invert each other, the x and y swap places. That means that the domain of inverse g is equal to the range of the original function, right? So the range of the original function gives the domain of the other, because obviously y equals this, that's y here. So the domain is essentially the y, because they switch places here, okay? But we did work out the range in part B. Well, the range is this, so the domain is now just simply going to be 2 less than x less than equal to 15 over 2. Cool. And that should be your answer to part 1. The first, oh god, so I'm not gonna lie, not the nicest question to ease you in. The first part A, obviously quite nice. Inverting it shouldn't be that difficult. But yeah, very part B especially can be quite tricky, especially because range is quite a tricky topic at A level. So yeah, not the nicest. Okay, let's see this vector question then. Okay, question 2. Okay. So it's given us 3 different position vectors essentially, and it says D is this. So I guess 4 position vectors in a way. So it's asking to find the position vector of D. Okay. Well, we are given A and B, and it's in terms of A and B. So I think we use that then. So let's have a look at what we're given for D. This is the only information we're given. A, B is B to D. Now, actually, you must remember the almost triangle law, so the vector one, which will always come in clutch for every vector's question like this. You should know AB saying OB minus O to A. You visualize this with the triangle. So say we have O here and a generic point A and then B. This is what's a triangle law. You form a triangle in terms of the 2 points and your origin O. Say that's O and that's A and then that's B. Well, that's AB. Go from A to B, but alternatively, we can go from A to O and then O to B. So that's the same as saying O to B minus OA. Because remember, the opposite direction is negative. So A to O is negative OA. So that's triangle, and that triangle law for vectors will come very handy. And that's what we're going to do here. So let's split this up using this. So AB is saying OB minus OA in terms of position vectors, which we're given here. Position vector, notice that's same as that is starting from the origin and going to the point. So that is OB, and this one is OA, and this one's OC. Okay, hopefully that makes sense. And yeah, so that's equal then. Well, B to D is OD minus OB. And actually, it says find position vector D. Well, OD then, if we rearrange this a little bit, that's going to be, if we add OB to both sides, that's going to be 2OB minus OA. And actually then, substitute it in. So so what's OB? So 2 lots of, and I'm going to do the column vector. So OB, well, that's going to be 4 minus 2 and 3. Remember how you can convert IJK into this. That is perfectly acceptable. And it makes it quicker to write. And then OA is 2, oh, yeah, 2, 3 minus 4. Bit slow here. Check that right. Should be. I think, lovely. And we just work this out, okay? So vector addition and subtraction, whatever, works in the way you expect. So subtract it entry wise, right? So 2 times 4, which is 8 minus 2, that's 6. 2 times minus 2, which is minus 4, minus 3, that's minus 7. And 2 times 3, which is 6, minus 4, so adding 4, so 6 plus 4, which should be 10. And that would be your position vector D. Okay. Cool. So part B then. So what's it saying now? It's given that the length AC is equal to 4. Find the value of A. Well, A's here, so it's a component of C. Well, again, we're going to do the same sort of strategy. So AC, because we're only given position vectors, let's split this up in terms of position vectors, right? So AC is the same as saying OC minus OA. And actually, that is equal to, if we put it in the column, OC is A5 minus 2. Minus OA, which was minus 2, 3 minus 4. Oh dear. Yeah, let's just work this out then. So this vector goes to A minus 2. We can't do anything more with that, just leave it as that. 5 minus 3, which is 2, and minus 2 minus 4. So minus 2 add 4, which should just be 2 again. And yeah, so that's AC, but it's told us that the magnitude of AC, which is this bar here, the magnitude, or the modulus, whatever you want to call it, there's loads of ways you can call it, that's equal to 4. That is basically saying the length of the vector is 4. Now, how do we work out length? Hopefully you should remember that mod AC is the Pythagoras of the distances, right? So that's going to be root of A minus 2 squared plus 2 squared plus 2 squared. Okay, so he's summing all the squares of the components together. Okay, and actually we're told that this is actually no. Let's simplify it first. So, well, this is the root of. We're going to have to expand the brackets, right? So that's going to be a squared minus 4a plus 4. Hopefully, you should be quite quick with that at this point. Plus 2 squared plus that's 2 squared 2 squared. That's 4 add 4, which is 8. Which again simplifies to a squared minus 4a plus 12. Cool. Now we are told that this is equal to 4, right? So equate this to 4. Okay, okay, cool. And actually, if we have a square root, we can just square both sides. So that means a squared minus 4a plus 12 is equal to 16. And then we could, this is a quadratic to solve for a. So that means a squared minus 4a minus 16 minus 4 equals 0. Cool. I'm going to be lazy now and just put this in the calculator. So to solve this, what's the solution here? 1 minus 4 minus 4. Yeah, and it gets you a nasty square root. So it's saying a is equal to 2 plus or minus 2 root 2. Okay, so we've got two solutions. That might be okay. What else does it tell us? There might be some information here. So a is a constant and a is less than 0, so a has to be negative. That's our key input here. So to find the solution to accept, so we need to note that a is less than 0. So a has to be the negative, right? So 2 plus root 2 is positive because we're adding two positive numbers. So it's going to be 2 minus 2 root 2. And that's the exact answer. Does it say to decimal points? Always check that. But no, it just says the value of a. So that should be the value of a there. Cool. And yet to double check, that's about, you don't need to write this, but that's about minus 0.83. So that sounds fairly reasonable. I don't know. But cool, so that's the answer. Cool, part 3. Proof. Cool. Okay, so M and N are irrational numbers. Then the product is also irrational. So irrational, you need to know, means cannot be written. So an irrational number, I should say, written in the form A over B, where A, B are integers. So that means your stuff like pi, root 2, all that good stuff. And a recurring decimal, no, not a recurring decimal, surprise, but a decimal that goes on forever. So 1.675338, something like that. So those are the example rational numbers. Okay. Well, actually, I think an easy one perhaps to spot is actually take M to be E and N to be the inverse of E. Now that's 1 over E. But that still isn't irrational because E is a number and E is not an integer. E is like 2.7 to something, I believe. So that's irrational. So this is not, even though it's a fraction, it's not what's it called? It's not a rational number because the E is obviously irrational. And actually, I think that's the easy thing to spot here. So take the inverses of each other. Then Mn is E times e to the minus 1, which is E times 1 over E, which is E over E. Well, actually, they cancel out, and that just leaves us 1, for God's sake. Actually, which is 1, which isn't irrational, but 1 isn't irrational. Therefore, the statement is false, because we use an example to show that this isn't true. Okay, so that's the idea of this. So you use the initial assumption that you take two rational numbers and they're not equal to each other, which clearly isn't. And you should actually make that quite clear. And E clearly cannot be 1 over E. Okay, seems very obvious to write, but that's, you have to be quite careful with proofs like this. But yeah, make sure every part of the hypothesis, that every part of the conditions they give you is true. And E not equal to 1 over E. Cool. And so yeah, so we make sure every part of the condition is true. So the numbers are not the same and they're irrational. They're both irrational. But actually, we just then show that this cannot be true. The conclusion, right? Mn. So yeah, that's the idea that I think for part A. Okay. I guess it can be a bit tricky, but I think if you start to consider inverses, then you get stuff like this, maybe. You could also easily take pi. So you could have pi and then pi minus 1. And yeah, cool. I think you could have root 2 as well, couldn't you? So like root 2 and 1 over root 2. Well, that'll simplify to root 2 over 2. Well, a multiple of root 2 is still irrational. But anyway, those are something. I think that's like the most apparent type of examples to take here. But obviously, there's many more creative ones. But don't be creative in an exam like this. Don't try and think of like the absolute quackiest example. You don't need to. Just get the marks and move on. You know. Now's not the time to be clever. Just try and make sure you get it right in ample time. Anyway, so hopefully that makes sense. So that's the whole idea of count example. So then it says for part B, now, to sketch the graph y mod x plus 3. Well, actually, I kind of like considering this as like transformation of graphs. So you know how we have stuff like f of x plus 2 minus f of x, f of 2x minus 4 or something. and stuff like that. So obviously, what the idea is, you sketch f of x, and then you do them in part by part. I like to consider mod x as a distinct type of transformation. So what do I mean by this? Well, sketch x first. So y is x. It should look like this. But then again, then do mod x. So mod x, if mod x is essentially the graph reflect that when the graph goes negative, negative y, it rebounds. It reflects on the x-axis. It goes up. So obviously the when it's positive. Oh God, not from there. When it's positive, great. It doesn't say the same because obviously if you're mod x in y can never be negative here. So where the parts where it originally is negative, it just goes up like this. And hopefully it should be oh, it looks a bit curvy, don't it? It looks like that. So we just reflect it up, okay, away from the negative x-axis to the positive one. So it's kind of like that. So that's how I like to see, like sketching modulus functions. Just kind of treat it as a transformation of the graph. The transformation being reflecting the negative parts up. And so yeah, and then we add 3. So therefore, y is mod x plus 3. They shift the whole graph up by 3 units. So obviously, originally it intercepts at 0, but now it's just going to intercept at 3. And it'll have this sort of shape. And that should be your graph, okay? Cool. And then it says for part 2, explain why. What's it say? Explain why mod x plus 3, so our graph here, is greater than or equal to mod x plus 3. Okay. Well, originally, you put, well, at first, you might, oh God, it's a bit weird. Kind of looks like a triangle inequality, but anyway, moving on. So you might think, oh, where do I go? But they give you this part 1 for a reason, right? And it looks very similar to what we did before. So maybe it's asking us to consider the graphs. So I think it's a good idea to sketch the 2 graphs. So what is mod x plus 3? So actually, what does y's mod x plus 3 look like? Well, again, like do it part by part. So y is x plus 3. Wow. Well, we said that y could. Oh God, I can't draw properly. That's y is x. It needs to pass through the origin. I can't sketch on this. It looks like a curve. Ah. I can't draw. I really can't draw. Somewhat vaguely like that. Right? Y because x. Right. Hopefully, you don't know what that looks like. So y is x is there, and then we want to get x plus 3, and so again you're shifting it 3 units up. So look, and it'll pass through the x origin, the the x-axis. Well, at -3, right? So because -3 add 3 gives us 0. So 3 and -3. Oh God, that's rubbish. Oh, no. Okay, yeah, say that is our graph then, right? So that's 3 and that's -3 here. Okay, oh, I forgot to say, it's all gone now. 3. Obviously, do this with a ruler. The problem is I don't have a ruler and I don't have a fucking stable writing pad either. Okay, so it's vaguely like that then, I guess. Very vaguely. So that's 3 and that's -3. Okay. And then you want to modulus it. So like I said, treat it as its own transformation. So where does it reflect on the x-axis? Well, at -3, instead of going down, goes back up. So it looks like that, and then it goes back up. As usual, this part of the graph, because it's above the y-axis, sorry, when y0, the positive part, it will stay the same. So it looks something like that, right, at 3. And that is your graph y is mod x plus 3. Now, actually, because we draw on the other graph in part B, and we know what it looks like, why don't we then combine the other graph, which is here? And cool. And that's what we're going to do. So the graph we saw in part B looked like this. Okay, and actually, it's going to be this graph here, right? The so obviously, look, it gone here on the left, and it will go up here because the gradients are the same. Here, because notice this are like two equations of lines here, mx plus c, but obviously the gradient, but the gradient's 1 on either line, right? So if the y-intercept is the same at 3, and if the y-intercept is at 3 and they both go off here, they're gonna go off. They're gonna be the same line, aren't they? Because the gradient is also the same at this part, right? So they're going to be on top of each other, so they're going to be identical at this point. However, at the left, obviously the gradient is 1, so there's going to be like a difference of 1 between them at every point on the left. So mod x plus 3 here, this part of the graph will always be strictly above mod x plus 3 here. So actually what we can conclude is after... So let's write this in words, I guess, a little bit. So I'm not being too rigorous here, but I'd say something like after x is 3, the graphs y is mod x plus 3 and mod x plus 3 not coincide, are the same, right? As both gradients of lines are 1, or the same. Both gradients of the lines are the same. And and intersect at 3. The reason why that's important again is if they both start at the same starting point and then they're both the same gradient, they have to be the same, right? They go up by the same amount because that's the whole idea of the gradient. So they're the same. And before x is minus 3, 3, sorry. What do I want to say? By sketching the graph, or by sketching, we can see mod x plus 3 is above. That's not a bit unnecessary. Is above mod x plus 3. And that is because obviously the graph continues on to the x-axis, but here it doesn't go below 3. Therefore, mod x plus 3 has to be less than or equal to mod x plus 3 for all x. Okay, so for all values of x. Is that what they're asking us to prove here? Yeah, mod x plus 3 is greater than for all real values of x, which is exactly what we can see, right? So again, they asked us to sketch the graph in part B in the first part, so we're going to have to probably consider graph then, which is exactly what we've done here. A little wordy explanation to make sure you pick up the marks. That's so much I think they'd expect. There's probably a way you can make it a bit more rigorous, like a lot more precise, is what I'm saying. But I think you'd be okay for A level. I hope that makes sense. Right, I know this can be again like a tricky topic, graphs and proofs. But I think that's the sort of strategy of thinking about it, I'd say. Hopefully it made sense, right? Uh, but yeah, I was going to say a distance of 1 here. It doesn't really matter. But yeah, so that's the sort of thinking, right? As long as you, as long as you sketch you probably even I think that would be okay as long as you sketch both lines or graphs on the same graph, and then obviously you can clearly say that one line is always above another, which is what's happening here. Okay, so that's part 3. A bit fiddly, but hopefully not too bad. Okay, question 4. Sequences and series. Lovely, lovely. We got this question here. So it's saying, show that 16 r equals 1 of 3 plus 5r plus 2r is equal to some number here. Okay. Uh, so obviously we're going to have to work this series out. Now this notation, hopefully you realise we're summing all of this. So we're substituting r is 1, r is 2, r is 3, r is 4 until 16, and we're adding them all together. So that's what this sum means here. Like a weird S symbol for sum. Okay, it's sigma. That's what it's called. Both of you should be aware of that. So there are two ways. Well, there are multiple ways of doing it, really. One way, perhaps you can kind of 5R here. One way you can spot is actually this is an arithmetic series because it's in the form of a plus uh, nd. So this is an arithmetic sequence, or n minus 1. It doesn't really matter. Obviously, if we expanded it out, minus d is a constant, so that'd be absorbed into the a, so it doesn't really matter here. So it looks like this, right? A plus nd. Obviously, n is got r here, so yeah. So this bit is an arithmetic series, and this looks like a geometric. So one way you can split the series up into this. 3 plus 5r. Oh god. Plus the series of 16 to r equals 1 of 2 to the r. And they're exactly the same. You can split up any series like this. Okay. Um, and then you realise they're arithmetic. Or what you could do is substitute the first two values of r in and see what happens. So r equals 1. So then you'd get un, I guess. If you said that ur is 3 plus 5r plus 2 to the r. This is another way of looking at it. So then u1 would be 3 plus 5, lots of 1, so 8 plus 2 to the 1. So that's 10. 3 plus 5, 8 plus 2 is 10. u2 would be 3 plus 5 times 2, so that's 13. 13 plus 2 squared, that's 4, so that's 17. U3 would be, what, 3 plus 15? If you substitute r is 3 into here. 3 plus 15, which is 18, plus 2 cubed, which is 8. So 8 plus 18, was it? Which is 26. Yeah, I guess you see what happens. Uh, well, there's not an emergent pattern here, right? Obviously, this is the formula, but we can't simplify this, can we? So there's nothing apparent going on here. But what you could do instead, you could do it turn by turn, like piece by piece. So don't do it as a whole. Say that this is 3 plus 5 plus 2. U2 would be 3 plus 10 plus 4. U3 would be 3 plus 15 plus 8. U4 then will be 3 plus 20 plus 2 to the 4, which would be 16. Now, hopefully you measure, this is a constant, and then this is a common difference, right? We're adding 5 each time. So this bit is an arithmetic sequence, and this bit is geometric. You keep timesing, going up in twos rather than adding. You're timesing, okay? And so this little bit at the end is a geometric, okay? And so yeah, and that's exactly what we're doing here. So either way, if you try and plug values in, see what happens, or you immediately recognise what the arithmetic and the geometric part is, you should split it up into two different series, right? And that's what we're going to do here. Okay, so yeah, and obviously, like I said, if you were to substitute and just get directly get one number out, it's not a pattern that's emergent, right? You get it's not a sequence that's obvious. So then try and think about it in a different way. So again, think about what we've got here, or try and instead of substituting like just getting one number, try and substitute all the terms in and see if you can split it up. Okay. That's the idea of a series. It's, if you've got a complicated one, split it up and see what happens. Anyway, I'm going to stop waffling. So yeah, that's what we're going to do here. Well, this is an arithmetic. And here, again, if you wanted to, you could, if you're a bit unsure of like where the starting point is or what the common ratio is or stuff like that, substitute the first values in. So R is 1, like I said, at 3 plus 5R, that's going to be 8, 3 plus 5. 3 plus 10, so when R is 2, that will be 13. Um, and then it'd be 18, and then 23. And actually, to spot the common ratio, the first term would be 8, and the common ratio D would be 5. And so then we can work out a series for that. So you should remember that the series of the first n terms of a arithmetic sequence is n over 2 of 2a plus n minus 1 d. And that's what we're going to do here. So Sn is going to be n over 2 of 2 lots of 8, because that's a, plus n minus 1 of 5. Okay, because yeah, and that's it. And actually, so what's n? So n is how many terms we have. Well, actually, there's 16, right? So n is 16 here. So we want the sum of the 16 terms, which is 16 over 2. 2 times 8 is 16, and then n minus what? That's going to be 16 minus 1 times 5. And actually, you can bunk all of this into a calculator, and you should get. Oh, got syntax error. Why is that? Okay. Okay, I must have a bracket. Apparently that's 7 to 8. If we plug that in, this formula in, but there we are, right? So that's this series. What about this series? Well, again, you can consider the first three terms, right? So 2 to the 1, that's 2. Uh, and then R is 2, 2 to the 2 squared is 4. 2 R is 3, 2 cubed is 8. R is 4. R is 3, so R is 4 is 2 to the 4, which is 16, and it goes on. And this is a geometric, right? Which you can see here. You should have spotted that. And so yeah. So again, like with this, what is our first term 2? What's our common ratio? What we times in by? Well, that's 2, right? And how many terms we're going up to? 16. And likewise, you should remember that Sn, and actually, no, you don't need to remember, actually, this formula is in the formula sheet. If I get it up. Here we are, I'll see it down here. It's here, right? This first bit here. Sn is a of 1 minus Rn to 1 minus r. It's a geometric series, right? So Sn, if I just copy the formula, which is a of 1 minus r to the n over 1 minus r. Okay, well then that means S16, if we substitute all our numbers in, x16 is 2 of 1 minus 2 to the 16 of, oh no, sorry, make it a bit clearer, hang on, equals 2 over this, 1 minus 2. Again, plug that in, see what you get. 2 of 1 minus 2 to the 16 of 1 minus 2. And apparently you get this number here, 131072. Okay, and therefore we're going to add them. So the original summation of 3 plus 5r plus 2 to the r is adding these two together, right? 728 plus 131070 gets you what? 131798. Is that the answer they wanted? Yes, 131798. Lovely jubbly. So that's how you approach that. Yeah, and that's the idea of these series of questions. Well, for A-level maths, there's only a very limited amount of series you need to know. That's geometric and arithmetic. So if you're going to sum stuff, most pretty much that's what they're going to want you to do, right? Split it into an arithmetic or geometric one. That's the method behind that. Okay, cool. Okay, we're on part 2 now. Slightly different one this time. So what's it telling us here? A sequence of UN is defined by this. It's a recurrence relation, right? With this and U1 is 2 over 3. Find the exact value of the sum of the first 100 terms. Now that's a lot. So obviously the best idea, and also just to say, the best idea for all sum questions, what you should never do is just find all the terms and add them up manually. Do not find 100 terms and then add them all up. No, don't do that. I'm not even sure in theory you'd get the marks for that, even if you did spend the time on that. Don't do it. Okay, that's not the method here. Uh, okay, but it's a bit weird. This isn't a series we know, at least not apparently. With recurrence relations, the strategy always, because it's an unknown sequence, is to see what happens. Plug in the first few values and see what happens. Okay, so we know that un plus 1 is 1 over un, and it said the first term was 2 over 3, was it? Let me double check that. Yes, there we are. Yeah, so U1 is 2 over 3. What's U2 then? Well, it's going to be 1 over 2 over 3, which is 3 over 2. U3 would be 1 over 3 over 2, which would be 2 over 3. And actually then U4 would be 1 over 2 over 3, which would be 3 over 2. And we'll get this pattern, won't we? We'll just keep getting the same amount, same numbers each time. And you should realise that when a sequence flips like this, alternates between the same few values, it is a periodic sequence. And how many distinct terms there are is called the period. So the period is 2. So there are only 2 terms the sequence alternates between, which is 2 over 3 and 3 over 2. When it gets to the other one, it flips. Okay, so the period is 2 here. Okay, why is that important? Well, because if we know what the terms are between, we can somehow infinitely many of them. Because there's a pattern we can spot here. So the first 100 terms between r is 1 and 100 of u r, is it? Was that the question? Yes. Well, write this out. So we know that's U1 plus U2 plus U3 plus U4 plus dot 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 plus U99 plus U100. But actually, we know if we look at here, U1 is the same as U3 because it's period 2. Every 2 times, the sequence returns to itself. So 2/3, then U3 is 2/3. So actually, every 2 terms, it's the same one. So you want U1, U3, U5, U7, U9, U11, and it can, obviously, hopefully, you can spot it's every odd number, right? Every odd number, um, it gives the same result, okay? And likewise, every even result will give us a different one. So we can split this up like this. You don't have to write this though. And yeah, so I guess the only tricky bit here is how many terms are we going from U1 to U9? Uh, well, how many terms? Well, it's going to be the same amount, right? Uh, these two separated sums will have the same amount of terms, right? Um, well, how can we work that out? We know there's 100 terms in total, so half of that, because we're splitting it to odd and even, is 50. So this is going to be 50 lots of this, of each one, and 50 lots of these. Because each of these is the same, now U1 equals U3, which is 2/3. And the even ones, U2 and U4 and so on, give 3/2. And there's 50 lots of these. This is the sum we're doing, right? And just bung that into the calculator, and you get 325/3. And that should be answer to that. So whilst it's a huge number, if you don't panic, because the strategy will always be consider what the first few terms are, and you'll always spot a trick. Okay, and most of the time it'll be a periodic sequence, right? It will alternate and it'll have a period, right? So it will only flip between the few same terms, and then you can kind of split up the series like this. So split up to the terms that are the same, okay, and then add by the total. There you go. Um, and yeah, hopefully it makes sense. I think that's a fairly standard sort of question. There's a bit of problem solving, but question that's this is sort of a typical series question, if I'm honest. So hopefully we practice. Hopefully it should make sense. Hopefully. But yeah, so that's that. Lovely jubbly. Question 5. Actually, let me just look at the chat. Actually, I haven't seen the chat all this time. Am I missing something? Any comments? And by the way, if there is a question, I'll try my best to answer. Um, okay. Someone's saying hello. Hi back. Okay. Question 5. And we're given this equation. This equation has exactly one real root. Okay. Well, it says to show that from this equation, the Newton-Raphson formula can be written as this. The Newton-Raphson, you must remember, states this. Actually, I don't think you need. I'm pretty sure this is in the formula book, isn't it? Let me have a check. No, you don't. I know it gives you it in the formula book. So the Newton-Raphson iteration. If you have a function set to 0, this is the process. So xn plus 1. So xn plus 1 is xn minus f of xn over f dash of xn, I believe. It's not the worst thing to remember, but you don't have to remember it. So if you have a brain fog, don't be afraid to look at the formula book. But make sure it's very important you learn what you must need to learn, and the formula book doesn't give you it. and the stuff that you don't need to learn. So there's some derivatives. Normally it's certain trig ones. So I think they give like the derivative of tan and sec and all that sort of stuff. But most derivatives you need to learn. But you also need to learn how to derive it. Well, anyway, certain formulas you don't need to know, and the Raphson's actually one of them. So really, it's just a substitution exercise, I guess. But yeah, so this is our function here. So remember, for this to work, we have to have f of x, our function we want to find the roots of equal to 0. So this is going to be your f of x, right? And the roots are when f of x is 0, which is what we got here. Well, we need to find f dash of x. Now, actually, this is very nice because it's just a simple polynomial. So remember when you differentiate uh, a quadratic term, not a quadratic, a polynomial term like this, you just times by the power, so an x, and then knock one off. Okay, and that's what we're going to do here. So we're going to differentiate term by term. So 2x cubed, 3, the power times the 2, which is 6x, and knock one off. So 3 minus 1 is 2. Likewise with x squared, so 2 times 1, 2, and then knock one off. And the constant will go to 0. Okay, so that's our derivative. Yeah, and so essentially, that's what we've got to do. So xn plus 1, then, if you substitute it in, is xn minus f of xn. So we can notice there's no f of. So we're going to have to substitute f of x directly. And it's in terms of xn. So we're going to need to substitute xn in via our formula. Okay, so f of x is this. So xn is simply replacing all the x's with xn. So that's going to be minus 2x cubed n plus x squared n minus 1. And then the derivative, so substitute xn to the derivative function, which is 6x squared n plus 2xn. Cool. Okay, so we want it in this form. Well, notice it's only as a single fraction. So the best idea is to write this xn into as a single fraction. So how are we going to do that? Well, we want a common denominator, don't we? Well, this is the same as saying I'll just put xn of 6xn plus 2. So we don't need to times by another xn, it's already there. So we just times by the other bit, right? So 6 of xn. No, sorry, no. Ignore me. I'm waffling. No, so let's just do it normally. So with any fraction, you subtract them times by the denominators of each side. The denominator here is 1. So we're going to have to times by the whole shebang, right? 6xn squared plus 2xn. Minus this. Now, this is over 1, so we don't need to times by anything. If we times by 1, well, that's just itself. So you combine the fraction like this. Hopefully it shouldn't be too tricky at this point. Minus, and then this bit, 2xn cubed plus xn squared minus 1, all over the same fraction denominator. So the common denominator, which is 6xn squared plus 2xn. Yeah, so I guess now it's just expand and simplify, right? So this is 6x cubed n plus 2x squared n minus 2x cubed n plus x squared n minus 1, all over the same denominator. 6x squared n plus 2xn. God, loads of n's. And we can collect like terms and simplify, right? So there's an x cubed term here, 6 minus 2, which is 4, x cubed n. There are two x squared terms, 2 add 1. And it's minus 1. Okay. All over 6x squared n. There's nothing we can do at the bottom, so let's just leave it as it is. Okay, it doesn't seem like we can do anything else. So let's check with the final answer. Is it in the form? 4x cubed plus x squared. Well, we've got 3x squared, so something's gone wrong there. Over 6x squared n plus 2. Well, everything's right apart from this. So let's have a check what we've done wrong. It could be we added the wrong sign. So let's have a look. Okay. Oh, here. Oh, hang on. Hang on, is that plus 1? Ah, it's plus 1 as well, yeah. Well, I noticed I didn't put the negative into here. So when you combine it with 1, you have to minus everything. What I did here was just minus the first bit. So you times in the top bit by minus 1, so that's minus 2x there, 2x cubed, minus x squared plus 1. Okay. So what we have here is 6x cubed plus 2x squared minus 2x cubed minus xn plus 1. Okay. So just a sign issue, I guess. Check your working. And then you get 4x cubed, which we've got 2x squared minus x squared, we just plus x squared. Uh, as so, and then plus 1. Is that the answer they wanted? Let's have a check now. So now that we've checked that working, is that right? Yes. Lovely, lovely. That's the beauty of these show that questions. If you make a silly mistake and you don't get the right thing, it allows you to check your answer. Okay, so that's part A. Now it's saying, using the formula in part A, find the values of x2 and x3. Very, very nice question. So, and that's part B, not part A. X1 is 1, right? Yes, so x2 then, we just substitute it in. So x2, and I don't really think you need to show your work in here, but I guess it's safe to do so. All you're doing is substituting it in. So this is xn, remember? Xn plus 1, sorry. Well, x2, if you substitute it into here, that's n is 1 here, so 1 plus 1 is 2. Well, that's going to be 4 of 1 cubed plus 1 squared plus 1 over 6 of 1 squared plus 2 of 1. And that's what you want to put into your calculator, right? So it's a fairly simple iteration question, right? So bung that into the calculator. And apparently you get 3 over 4. And then we're going to do the exact same thing here. X3 is going to be 3 over 4 cubed plus 3 over 4 squared plus 1 all over 6 of 3 over 4 squared plus 2, 3 over 4. And that will get you... that would get you 2 over 3. And actually, it kind of makes sense, doesn't it? Because it's clearly converging, right? So 1 to 0.75 to 0.66. There's clearly we've done something right here, hopefully, because our answer makes sense, right? And that's the idea of the iteration formula. It converges. Okay, so part C says explain why the Newton-Raphson method cannot. I need to charge my battery, my laptop. Bloody hell. Explain why the method cannot be used for the initial value x1 is 0. Well, very simple. So if you're using the method, you're using the formula here. But what happens if you substitute x1 is 0? And you can kind of spot this immediately. But if we substitute x1 is 0 into the formula, well, notice here, right? Notice here you'd have 0, 0, add 1, 1 over 0, add 0. Well, 1 over 0. But that cannot happen because you cannot divide by 0. So the denominator is 0. is 0. Hence, uh, well, it's undefined. So we cannot use it. We cannot use this value. And that's it, right? And that is really one of the main flaws in Newton-Raphson method. And I have a feeling they might potentially ask, why could you not, for a Newton-Raphson method, why could you not use f of dash x, a stationary point, sorry. Say if x is a stationary point, why can you not use x as a, and actually x is 0 is a stationary point, because f dash of x is 0. Why can you, in more generally, why can you not use a stationary point as as a value, right, to sub in? And the whole idea is f dash of x would then be 0 because it's the whole definition of a stationary point. So it'd be undefined because obviously the whole fraction is f of x over f dash. And if this is 0, the denominator is 0, so it's undefined. So be careful. They might ask that as like a 1 marker. Just make sure you're prepared for that. But yeah, that's really the main limitation. Obviously, you have to make sure there's convergence. So make sure the point is reasonably close to the solution. But yeah, that's mainly the main issue you got to be prepared for. But yeah, that's that question. Very, very, very nice question in my opinion, especially after the earlier ones. Okay, one question 6 now. So part A, what's it saying? Calculate f of 2. Oh, wow, that should be fairly straightforward, right? GCSE question. That f of 2 for, well, not 3 marks, but it's this. I already suspect I know what this is going to go to, but let's work this out. Well, f of 2, just substitute it in. So minus 3 of 2 cubed, replace x, plus 8 2 squared, minus 2 of 9 of 2, plus 10. What does that get you? Well, again, substitute in the calculator. Minus 3 of 2 cubed. And my prediction is actually this will go to 0 based on the next part of the question. Yes, and it does. F of 2 equals 0, which is good. Because actually, what does this tell you? If x is 2 is a root of f of x, x minus 2 is a factor of f of x via the factor theorem. This is important because it's saying now to write as a product the two factors. So that's what your brain should be linking to, right? We have a root equal to 0, and we have and it's asking us for factors. That screams factor theorem, okay? So therefore, that's saying f of x is x minus 2, and actually, look, it's a cubic, right? So it's x cubed. So if we have a linear term, to get a cubic, we're going to have to times by a quadratic term. That looks like this. Okay, there are two ways to find this. You can divide f of x, which is this part here, by x minus 2, algebraic division, and then that gives you the quadratic straight up. Or you could substitute some values in. So that's what I think that's the best way to do it. So minus 3x cubed. Let's write out f of x plus 8x squared minus 9x plus 10. And it's going to be equal to this here. Ax squared plus bx plus c. And the idea is we need to find missing a, b, and c values. Okay. So the way to do this, the best way is to compare coefficients. So by comparing coefficients, And what I mean by that is the coefficients of each term, right? X cubed, x squared, and they have to be exactly the same, right? So let's have a look at minus 3x cubed here. So let's look at the x cubed term first of all. That has to be equal to, technically identical to, but it doesn't really matter. They're not that pedantic over it. And that's equal to, how do we get x cubed here? Well, the only way is to times x by ax squared. So that's going to be ax cubed. Therefore, clearly by observation, a has to be minus 3. Okay, now let's go to x squared. So minus 18 x squared here. It's a bit messy, I apologise here. Let's write that a bit clearer. 18 and 9, that's okay. Plus 10 here. Oh god. There we are. Okay, so minus 18 x squared. How are we going to get an x squared here? Well, you're going to have to do times ax squared or minus 2 and bx by x to get bx squared. There's no other way. A constant? Nah, there's no other way. Oh yeah. Well, actually, this means minus 18 has to be minus 2a plus b. But actually, we know that a already is minus 3. So that is equal to minus 2 times minus 3, which is 6 plus b. Therefore, b is minus 18 minus 6. That's minus 24. And okay, cool. Now, there's one more term you need to compare. There's only one more missing value. Now, you could compare x, right? But I think the best thing is to compare the constant at the end. Because again, there's only one way to get the constant here. And the constant 10. Well, there's only one way to do that, and that's going to times the constants here, right? Minus 2 times c. So that's going to be minus 2c. So not timesing by any x's here. Well, that means that therefore c has to be minus 5, right? If you divide by minus 2. So therefore, our factorisation is f of x is x minus 2, and then substitute our values of a, b, and c in. That's minus 3x squared minus 24x minus 5. Okay. Cool. I believe, hopefully it should be right. Uh, let me check this. Uh, oh God. Yeah, I knew it was a bit. Yeah, I knew that was a bit weird. Okay. Uh, oh, that's what. I copied it down wrong. It was meant to be plus 8. I somehow got minus 18. It's plus 8. So I just copied it down wrong. I will say in my defense, because I'm writing, like I have to keep scrolling and writing on the digital pen. I wouldn't be like in the exam hall and see all the questions in front of me, so I can easily copy and transfer. It's really awkward. I don't make mistakes like copying down like this normally. Uh, but yeah, that's just my defense. So yeah, this is wrong purely because I copied it down wrong. But the approach is the same, right? So instead of minus 18, it's just 8. Okay. So 8 is equal to this, so we know that 6 is equal to b, so b would be 2. So it's 8 minus 6 would give us 2, not minus 24. I thought that was a bit of a weird number, that's why I double checked. By the way, if you are unsure, don't be afraid to double check, right? And that should be your answer there. That's your it said factors, right? Not linear factors. Yeah, just two factors, right? You don't need to factorize the x squared term. You might not be able to, but just leave it as that. That's two different factors. Cool. Okay, we got rid of that. Okay. Now it's saying using our answer, prove there are exactly two real solutions to this. I'm going to jot this down. Minus 3y to the 6 to the 6 plus 4y to the 4, was it? Or was it plus 8? Yeah, plus 8y to the 4 minus 9y squared plus 10 equals 0. Is that all right? So again, like I keep scrolling because I can only see one page at a time, and it's a little bit unclear at times. Yeah, that should be the right equation. So it's saying to use it to show that there are two real solutions. Well, notice how f of x, our original, was minus 3x cubed plus 8x squared minus 9x plus 10. That was the original f of x, right? Here, minus 3x cubed plus 8x squared minus 9x plus 10. Notice the difference. What are we doing here? So the x's and the y, the variables don't matter. But what essentially, how we get here is saying y is x squared. All we're doing is doubling each power. That's all we're doing. So then if we substitute this into here, or I should say actually more specifically, x is y squared. Yes, because then if you substitute y squared into here for x, you'd get y squared of cubed, which should be y to the 6th, x squared, which is y squared squared, which should be 4, minus 9 y squared plus 10. So this is what we're doing here. So what we should do is perhaps use our factors here to say, well, if we say this is f of x, well, f of y, or f of y squared, sorry, because in replace for x is y squared, well, we know this factorization, don't we? This is another way of expressing f of x. But if we just substitute y squared in for x, which is exactly how we get from this root to the other, this equation to the other, well, x is y squared minus 2, and minus 3y to the 4 plus 2y squared minus 5 equals 0. Okay. But actually, all we're doing here, because we're just essentially squaring everything, if we might be able to actually never mind. We're here, right? So this is saying y squared minus 2 has to be 0, or minus 3y to the 4 plus 2y squared minus 5 is 0. Well, we can solve this easily. Well, y squared has to be 2, which means y is plus or minus root 2. These are two real solutions. But what about here? Well, again, notice in a similar way, this is just essentially squaring this. The square of this, not squaring each term. Well, let's study. No, because it's saying there's only two roots, and we've got two roots already. Perhaps there's no roots for here, no real roots for this. Well, check this. Well, how do we check if a quadratic like this? And this is a hidden quadratic. You should be able to spot that, right? Again, this is a hidden quadratic. How do we spot if there's how a quadratic has real roots? You consider the discriminant, right? Uh, so I would say 4 minus 3y to the 4 plus 2y cubed minus 5. Discriminant is equal to b squared, which is 2, which is 2 squared, minus 4 of 4ac, so minus 3, and minus 5. What is that? Put that in the calculator. Well, very clearly it has to be negative, but let's just put it in. So 2 squared minus 4 of minus 3 minus 5 will get you minus 56. which is less than 0, which means uh, this uh, this what do I want to express? This function. Yeah, no, not function. This expression, which is minus 4y to the 4, has no real roots. Well, technically, what we are saying is the quadratic version. This has no real roots. That's a discriminant. But if this has no real roots, so if x has no real roots, and if y squared equals x, y also can't have real roots. Okay. So that's the sort of idea of this. So therefore, only solutions come from or arise, technically, more fancy, arise from y squared minus 2 equals 0, which is y equals plus or minus root 2, which has 2 real roots. Therefore, equation of 2 real roots has only 2 real roots. Okay. I think that's more than you'd expect to write, I think. But as for 3, it's 3 marks, I think. But the idea is, no, it's 2, I think. But the idea is obviously you substitute. You use the factorization, so then you be able to start to say this has 2 solutions and this has none, because perhaps you can use a discriminant, or you could argue otherwise to verify there are indeed no real roots. Okay, but that's all you need to say. But this is a bit. This is more or less just explain and drive home the point of what we're doing. Okay, but I've written a bit more than you should. Okay, but there's another part to this, and it's saying deduce the number of real solutions to this equation. Okay, I'm probably not gonna. I'm gonna write it over here. I can't. I'm a bit tired now. I'm just scrolling back and down, as I'm sure everyone else is. Okay. So I should probably say then the plot to it was x minus 2 and minus 3x squared plus 2x minus 4, was it? No, no, I think it's minus 5. Minus 3, 2, and minus 5, yeah. That will help us if we can write it clearly. Uh, so what I've done here is just copied the factorization. That's all I've done here. Okay, that will help us for sure. So it says deduce the number of real solutions to this for only 1 mark. Okay. And notice again, it's exactly the same expression, but we're just saying x is tan theta. So it's sort of the same thing, we're just substituting one into another. So therefore, f of x then, or f of tan theta, I guess more specifically, is 3 tan squared, this part here, right? So if you replace x here for tan theta, you get exactly this equation. Oh, you don't get exactly this, but you get minus it. So notice f of x is minus 3x cubed plus 8x squared. Here it's the opposite. All the signs are opposite. That doesn't matter because what you're saying there is you just put a minus out in front. Okay, so you could say that's equal to minus or minus f of x is equal to minus of this, right? So x minus 2, tan theta minus 2, and minus 3 tan squared theta plus 2 tan theta minus 5. And that has to equal 0, right? But obviously, if you divide by negative each side, you get rid of it. So we don't have to consider the negative. Okay, so therefore it's saying either tan theta has to be 2. Because there are no real solutions, as we just seen, because of the discriminant. there were no real solutions to this part here. So the only way you can get this is saying tan theta is 2. Now, tan theta can be 2. And more specifically, when does tan theta equal 2? Well, look at the graph, right? So the graph of tan theta looks like this. So 45 degrees is when it's 1. Or in radians, that'll be pi over 4. Okay. So then 2 would not be far off. But the point is, right, we don't need to know what the root is. We just need to know how many solutions there are. So this is, and then you continue the graph on here. You should know that tan theta repeats every 180 degrees, or repeats every pi. So tan of x repeats every pi radians, right? You don't need to write any of this because it's just saying state the number of solutions, but I'm explaining how you get there. Okay, but we know there's a solution in this interval, and then the next 180 here, that's when tan of theta is 2. Then the next 180, there's another solution here. Okay, and so it's saying between 7 pi and 10 pi. Well, where roughly is the first solution for 2? That's in degrees. I don't want degrees. Radian is 1.1. 1.1 radians. Okay, yeah, sorry, you don't need to calculate this. But you basically just need to look and see actually, well, it is between pi over 2 and 0. It's between 0 and pi over 2. Get rid of this. That is our solution here, right? That's where the solution is. If you see on the graph here, pi over 2 is the asymptote and 0 is there. So the solution falls here. So then, and obviously, if it's every pi radians, the first time it reaches this interval, it's going to be between 0 and 7 pi and 7 pi over 2. Okay. No, not 7 pi over 2. 7 pi plus pi over 2. Uh, 7 pi plus pi over 2. Okay, because we add in pi every time, and then if we can add 7 lots of pi to get into this interval. So there's one solution here. Then we can add another pi to get 8 pi to 8.5 pi. That's another one. And then another pi after to 9 pi, and then 9.5 pi. Then if we add, that's 3 solutions. Then if we add another pi after that, so 7 pi, 8 pi, 9 pi, 8.5 pi, 9 pi to theta to 9.5 pi. If you then add another pi, the next solution will be between 10 pi and 10.5 pi. But actually, that exceeds the boundary, right? It can only be between 10 pi. So there's only 3 solutions here that fit this interval. So the number of real solutions is 3. Okay, I know it might be a bit complicated, but obviously, but let me just double check that's right. Yes, there are 3 solutions. So I guess to go over that, I know it looks a bit of a mess now. I do apologise, but the idea is to match this quadratic to this, not quadratic, polynomial to this, because x is tan theta, and so you get the same one. If you substitute it into the factorisation, like we did with part B, you get this. So tan theta has to be equal to 2, because this other bracket has no real solutions. We've already seen that. So this is the only solution we can get for tan theta. And this solution lies, if we sketch the graph, between 0 and pi over 2. And because that also repeats every pi radians, every pi times, if we add 7 pi, because it starts at 7, we know that the initial solution is in this interval here. If we then add 7 pi to the interval, this is our first solution, right? And then the second solution, you keep adding pi each time. And then eventually you get out of the boundary, right? Out of the range. So these are the only three solutions in the range by adding pi, okay? So that's how you arrive to three solutions. Okay, a bit of a tricky question, but hopefully that's somewhat clear. So I'll just say three solutions here. Because what did you don't need to do any working for that. But that's the method and the thinking behind that, okay? Okay, and talking of trig, we actually got a trig equation now, by the looks of it. So 7i, solve for this equation here, this domain, this range of x. This equation for 4 marks is sec x. Now, with any trig equation, you need to somehow get it into the form sin x equals k, cos x is k, where k is a number, or tan x is k. We do not want a combination of stuff, and we do not want any reciprocal, so sec, cosec, cot. These when every single trig equation will boil down to solving this elementary equation, right? This we can solve by just inversing sine, cos, and tan. This is the whole idea with solving any trig equation, is to boil it down into any of these three forms here. Okay. So that's what we're going to do. So sec x, well, that's 1 over cos x. So right, again, the idea is to get it in terms of one of these three elementary trig functions. And what can we do? Well, we can times across by cos. So 4 sin x cos x is 1. Therefore, sin x cos x is a fourth. Okay, what can we do here? Because it's not equal to 0, so we can't just say sin x equals 0, cos x is 0. But notice we have a double angle. So you should know that sine of 2x is always 2 sin x cos x. Uh, Thus, if you substitute this in then, well, if 2 sin x cos x is this, then 1 sin x cos x is a half sine 2x. So that means a half sine 2x is equal to a fourth, right? If you directly substitute this in. Okay, you need to remember this double angle. The double angles you must remember. If you do somehow forget them, you can derive them, but it will take a bit of time. Because you are given the addition formula for the angles here. So sine of a plus b is this. Take the positive. But if you set a to be and b to be the same, so x plus x, that's sine of 2x. So sine x cos x plus cos x sine b, sine x, sorry. But that's two lots of sine, 2 sine x cos x, which is exactly the double angle we get there. So if you ever stuck, although you should ideally remember them by now, if you ever stuck, you can sort of derive them by the formula book. Use the addition formula and say sine of x plus x and substitute that in. Okay, but that is the double angle we're working with, just to clarify. Okay, just a little exam tip there. So yes, hopefully you can see why we've done that. Now it's actually in this form, because obviously it's not sine x, but sine 2x, but exactly the same, right? We can just change the angle. Okay. So yeah, so therefore sine x, sine 2x, sorry, again, get rid of the half, times by 2 to get rid of the fraction, and we get a half. And this is nice because this is a double angle. No, double is an exact trig ratio, sorry. Okay, but how do we solve this? Well, say for a sine x, and this is why it's really good and why you have to put it in one of these three forms. because we can solve it by the graph, because we know what sin x, cos x, and tan x look like. We can easily spot the graphs when they cross k, okay, the constant. But in this case then, so we want a half. So let's consider the graph of sin x. And we need to consider where we draw the graph from. So it's said between 0, x, and pi over 2. But we have 2x, so it's going to be between 0, 2x, and pi. Okay. So the part where the graph is pi is here, right? This is our endpoint here. Okay. So actually, we can just get rid of that little hump. So that's the only part of the graph we're interested in. Anything else, it's not pi, okay? It's above pi, and this is less than 0. Okay, so a half. Well, when it's a half, it crosses the graph sin x at 2 distinct points, right here and here. Well, you can use the calculator to inverse it. So what's inverse sine of a half? You should remember that. It is 30 degrees or pi over 6. That is called a principal solution. So the solution you essentially, not the same, but essentially the answer you get out the calculator, that is called your principal solution. It's called principal because you can work out all the other values from that one solution. And it's the closest solution to 0, okay? Anyway, so that's all you need to know. Inverse sine it. And then notice the symmetry around this little hump. It's going to be the same distance on either side. This solution here is going to be the same distance between here. Okay, it's symmetrical about pi over 2. Or you could say the distance between 0 and this angle here, which is 0 to pi over 6. Well, the distance was pi over 6. It's the same pi minus this. So to get this answer here, you do pi minus pi over 6, which is 5 pi minus 6. Okay, and also, by the way, if you are a bit unsure about if you got the right answer, just substitute it back in. So, what is sine of 5 pi over 6? And you should get a half, right? So if you're ever a bit unsure about if you interpreted the graph right to get a solution, just substitute your solution that is a bit questionable. Substitute it in, and you should get a half. We do get a half, so 5 pi over 6 is correctly the right answer here. And that is the only two solutions in the range 0 to 2x to pi. Okay. Was that the right range? Yes, it was. But that's a solution to 2x. We want x. But what we can do is simply divide by 2. So therefore, x is pi over 12 and 5 pi over 12. And those are our two solutions, okay? Yeah, so that's a very standard trig equation question. But what I've explained there is how you approach a typical trig equation. So I wrote and explained more than you should have, okay? But that is the essence of trig equations, okay? So I guess the only tricky thing perhaps is spotting that this is a double angle. But after that, it should be pretty standard. Okay, so that's 4 marks. Now we've got a different trig equation. So this time we have 5 sine theta minus 5 cos theta equals 2. And again, in exactly the same process, we need to sort of kind of get the equation into the form sin x equals something, cos x equals something, or tan x equals something, or a multiple of them. Okay, so we need to clean this up. But okay, how do we do that? Um, there's one way that immediately jumps out to me, uh, and that is the harmonic form. And And this is what I'm not sure they expect you to know this off the bat anyway, without some guidance anyway. But you can express any combination of sine and coses like this in the form r sine or cos, doesn't really matter, theta plus alpha. That is harmonic form. And that's exactly what we've got here. A is 5 and B is minus 5. And we can write it in this form, which is good, because this is now saying essentially sine of something equals a number, which we can solve. So that's the immediate way, but I'm trying to think, if we didn't spot this, is there another way you can solve this? I wonder. Uh, I'll come back to it, but this is the way I think probably the best approach. So that's what exactly what we're going to do. So we're going to say 5 sine theta minus 5 cos theta is this r sine theta plus alpha. What we're going to do is we're going to expand it. So it's kind of like a bracket to expand because we know the we know the addition angle formula. So that's going to be r of, well, what's sine theta plus alpha? Well, you shouldn't, it's in the formula book, but sine theta plus alpha uh, would be sine theta cos alpha plus uh, don't worry about the negative because that will work. That will reveal itself. We can deal with that. Anyway, so then that'll be cos theta sine alpha. Okay, if you that'll be in the formula book. Okay, I'm not going to get the formula book out now, but that the double angle is in the formula book, so you literally substitute theta and alpha into that. Okay, uh, and then we can expand. So that's r sine theta cos alpha plus r cos theta sine alpha. And what and this is identical, so they have to be exactly the same. Well, compare. So compare terms. So sine theta is here and cos theta is here. So we're matching. Well, the coefficient is 5. So that means 5 has to be r cos alpha here to ensure, and alpha's a constant, by the way, so this will all be constant. So 5 is this, and likewise minus 5 is going to be r sine alpha. Cool. So what do we do here? Well, if I label this 1 and 2, again, like this should be fairly autonomous process. Harmonic form uh, is in the book, and it is on the spec. The only thing I'm a bit unsure of is them expecting you to convert stuff into harmonic form without being told in it explicitly. You know what I mean? Because a lot of questions I see ask you first to explicitly convert this to harmonic form and then solve it, but they're not asking you to convert it. That's what I'm a bit unsure of. But I think the idea is to write it in harmonic form, and you should be able to do that quite quickly. That should be a fairly, at this point. Hopefully, you revised it, so this all bit should be completely natural. Okay, you don't have to do all this, by the way. You can immediately jump to finding R and alpha. But what I'm doing here again is explaining the process and the thinking. If you're ever stuck on how to do it, think back to like a way to like break it down. Anyway, so we label this, we've got two equations, two unknowns, but I think we can solve for r and alpha. Well, actually, if you know the these identities here, cos squared theta plus sine squared theta identical to 1. Wow, what if we square 1 and square 2 and add them? So 1 squared and 2 squared. Wow, that's going to be r squared cos squared alpha plus r squared sine squared alpha. And that's going to be 5 squared add minus 5 squared. So that's 25 add 25, which is 50. Cool. And actually notice we can group this up. So r squared of cos squared alpha, factorise r squared, equals 50. And this all then boils down to 1 because of this Pythagorean identity here. So therefore, r squared is simply 50. Which means that r is root 50, not minus 50. Okay. Because it's it's kind of like a length again. I think you might be fine either way, but you take r to be greater than 0. Um, but yeah. Okay, so that's r, but we also have alpha. Now, what other identity do we know? Well, we know that also tan theta is sine theta over cos theta. So I guess instead of squaring and multiplying, we're going to divide. Well, sine alpha over cos alpha, 2 divided by 1. That will get you r sine alpha over r cos alpha. That's going to be 5 over minus 5, which would be minus 1. And actually, this boils down, well, r and r cancelled out. Sine alpha over cos alpha here is tan. So tan alpha is minus 1. And you only need one solution for alpha, just inverse tan it. And actually, you get minus pi over 4. Lovely jubbly stuff. So we found our two values. So therefore, going all the way back to the original equation, you don't have to do all of this. I'm just sort of deriving it. But you should immediately jump to r, which is square rooting squares of this. Okay, the squares of the coefficients, and tan by dividing. Okay, but that's the sort of process. That's what's going on in the background. Okay, this is a sort of derivation behind the method. Okay, so we found our missing values. So jump all the way back to the original. So 5 sine theta minus 5 cos theta. 5 sine theta minus 5 cos theta. That is now identical to root 50 of sine of theta plus alpha. Alpha's minus pi over 4. Notice I said you don't need to worry about the signs. So notice here we have minus 5. You can still add plus or minus. The alpha will change. It will match. Okay, so it's minus here. It will all work out. So don't worry about the signs. All you need to know is r sine theta plus alpha. Cool. Now we are told, now we've done all that, that this is equal to 2. So therefore, root 2 sine of theta minus pi over 4 is equal to 2. And therefore that means sine of theta minus pi over 4 is equal to 2, no, root 50, sorry. Root 50 here. 2 over root 50. Which I guess simplifies to, if you rationalise, although you don't have to, it simplifies to root 2 of 5. Okay, so not the nicest number, but not the wackiest. Okay, so now again, literally, now again, look how we've got the form. Sine of an angle is equal to a number. So now we're in a position to solve it. Okay. So again, what's our angle? What have we got to work in? So what's that interval? Um, between 0 and 360. Okay. So 0 is between theta and 360. Therefore, but our angle here is theta minus pi over 4. So we subtract minus pi over 4. But actually, pi over 4, we're in degrees now. So pi over 4 is 45 degrees. Okay. So we subtracting minus 45 degrees. Okay, to each side. That's theta minus 45. Okay. So therefore, theta minus 45 degrees. I should probably change pi over 4 to 45, but it doesn't matter. Okay. Well, like I said, exactly the same process. So what's the graph look like? So sine of x or theta. Uh, oh, that's a rubbish graph. Uh, so between 4 minus 45 and 315, it would look something like that. Okay. Notice it won't go the full way to 360 because it's not 360, it's 315. Likewise, you have a bit of the negative bit. So that's minus 45, okay? Cool. So this has to equal root 2 over 5. So where's root 2 over 5? Let's arc sine it, inverse sine. And I need to put it to degrees. And that is 16.4299. That's our principal value. So it's saying it's about here, right? 16.4. And that is root 2 over 5. But where else does it cross? Again, here, right? That's the next solution. And that's it. There's no more solutions in this range, right? Those are the only two solutions. If we extend this, it will never cross because it only goes to 315. Likewise here, it will never cross on the left side either. So the only way then is saying if that's 16 and it's symmetrical about 90 here, we can get the other angle here, the solution here, by doing 180 minus 16. So 180 minus the answer gets us 163.5700 something. So those are our only two solutions here. Okay, so that means theta, you add 45. Okay, so theta would be 208. 0.57, which is this added 45. And we add this one by 45, so 16.4299 something plus 45 gets us 61.4. Does it say to how many decimal points or significant figures? It says giving your answers to one decimal place. Yeah, so, okay. So those are our two solutions, right? So to one decimal place, it's 208.657 rounds to 6. Cool. And this is 61.4. So those should be your two answers, right? Let me double check that. 61.4, 208.6. Lovely jubbly. So yeah, so that's the whole process there. Hopefully it made sense. Again, the trickiest thing with this, I think, is for part one, obviously noticing to convert to double angle, and for part two, to noticing to use harmonic form. Again, there might be another way of solving this, but I think that's the best way, and it's one you should be quite familiar with because questions often ask you to use harmonic form anyway. So that's out the way. What else have we got to do? Okay, one question eight. Oh, 10, 16. Okay, I won't be able to finish the whole paper. Oh, this has to be a two-parter, unfortunately. Okay, anyway, on question eight. So it says figure one shows a trajectory of a ball. The height is h above the ground and then plotted against the vertical distance x. It travels in the vertical plane. It just means it goes up essentially. Nothing to worry about there. The ball reaches a maximum height of 12. It hits the ground at a point 40 meters where it's kicked. So this gives like conditions, right? And it says find a quadratic equation linking h to x. So obviously, I even immediately realised from past questions this is going to be a quadratic modelling question. This looks like a quadratic curve, and it is. So it's asking us for a quadratic equation. So, well, the best way to start this off, and with all modelling questions like this, is to explicitly write down a general formula for it. So h of x is going to be ax squared plus bx plus c. That is a generic quadratic term, okay? So all this question now boils down to is finding these missing values. But notice we're given some information here. Okay, it's a bit messy there. This section here. We can actually label our graph actually. So um, it reaches a maximum height of 12. Well, the maximum's here, right? And it's telling us the height is 12. It doesn't say what value of x it is, but it's going to be symmetrical, isn't it? So if we can work out what this value is, we can halve it to get this. Because obviously, you should know that every quadratic is symmetrical or has a line of symmetry around its turning point. Okay, it's symmetrical on either side. But let's see what else it tells us. When it hits the ground at a point 40 meters, so the ground is here when h is 0, 40 meters when it's kicked. Well, it's not going to be here, is it? It's going to be here. It's 40 here. So x is 40 meters from when it was kicked. But now we know this is 40. This means this has to be 20. So we know two conditions. So what we know is actually when h is 40. No, sorry, when x is 40. No, I'm sorry. When x equals 40, h is 0. We also know, this is a coordinate as well, right? The origin. We also know when x is 0, h is 0. Don't forget that. And we also know when x is 20, here h is the maximum, which was 12. So actually, we've got three different points to substitute in. So we're bound to find A, B, and C. And that is the whole idea of these quadratic equation modeling questions. They love to always ask to model or find a quadratic equation in a context like this. And it's always the same thing. They also love to give you the intercepts, so the x-axis with the roots, and to give you some bits about the turning point. The main thing you need to know is that the turning point is a half of the roots, okay? The distance between the roots. So 0 and 40, if it's symmetrical, it's going to be the same distance between the two roots, okay? And so the idea is you get three distinct points, right, that you can substitute in to find your missing values, and that's all we're going to do here. Okay, so let's do the first one. So we know that h of 40 equals 0. So therefore, uh, 40 squared times a. Well, what's 40 squared? 1,600a plus 40b plus c equals 0. Cool. That's equation 1. And then we also know that h of 0 equals 0. Therefore, 0 squared plus 0 plus c. Well, c equals 0. And that's the second one. That already tells us one value. And we also know that h of 20 is 12. Therefore, 20 squared, which is 400, a plus 20b plus c equals 12. Okay, and that's equation 3. But actually, we know c is 0, so sub 2 into 1 and 3, into equations 1 and 3. So we know that 1600a plus 40b equals 0. And we also know that 400a plus 20b equals 12. Well, is this not simultaneous equations at this point? Now, I'm not completely entirely sure with the marking criteria of this. I'll check after this after solve it. But obviously, every calculator for A level should have a simultaneous equation solver, and it's only 3 marks. So I think if we this is 3 marks worth of work here. I do not think they need you to go through the hassle of actually solving it, substituting and stuff like that. You can do. Well, it's not hard. Actually, not hard at all. Um, we can times this by 2, and then we can subtract this from the bottom. So we can say 800A plus 40B is 24, and then subtract this, and then you get uh, 800A is minus 24, which means A has to be minus 24 over 800. So I'm subtracting this first top equation by this equation here, because I can get rid of 40b on both sides if I subtract the two equations. Hopefully that's clear. But yeah, you will be able to just put it into the calculator. I'm absolutely certain, but I will check the mark scheme after this. So A is minus 3 over 100. Uh, du- 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 du. And with modelling questions like this, it's normal to see like weird fractions like this. Okay, you're not going to get like nice integers. Okay, um, and yeah, so A is that, so that means B. Um, well, that means 20B then is 12 minus 400A. 400A is minus 3 over 100, which equals what? 12 minus 400 of minus 3 over 100 is 24. This whole bit is 24 in the calculator. That means B is 24 divided by 20, which is 6 over 5. And you can double check this using the simultaneous equation solver in your calculator. Let's check if I'm right. Yes, I get the same answers. Cool. Okay, so I'm going to check the mark scheme just to see where the marking points come from. Okay, so that's interesting. Okay, they really jumped the gun in the marking scheme. Perfect. Okay, perfect 0, 0. Okay, so you get a mark for finding that C0 and getting all the equations. Okay, so you get a mark if you assume, obviously, if you get a mark if you did it this way, which I think is the best way. In my opinion. I think the other parts of the marks, I think the way they did it originally is very unintuitive, in my opinion. I think this is the best way. But you'd only get a mark for getting these three equations, right, and the original model. So ax squared plus bx plus c. And then you deduce these equations, okay? You get 1 mark for that. Then, okay, so you then get a mark for attempting to solve, for solving it, right? So you do not put this into a calculator. You have to solve it. You have to manually solve it yourself. Uh, okay. And then obviously to piece it all together, h of x is minus 3 over 100 x squared plus 6 over 5x, and then plus c, which is 0. So that is your model, okay, which is your equation linking h to x, okay. Okay, yeah, the way the mark scheme does it is really weird, in my opinion. But yeah, I think that's the best way to attempt that sort of question, any type of quadratic modelling question. Okay, part B. So it says the ball passes over the horizontal bar of a set of rugby posts. So horizontal, obviously meaning a line. A line that's horizontal, right? That way. A set of rugby posts. And obviously a rugby, hopefully it kind of looks like this, I think. So you have to pass it over the bar here. Anyway. All you need to know is a horizontal bar. I've set a rugby post that are perpendicular to the path of the ball. Okay. The bar here is 3 meters above ground. So that's 12. The bar's going to be roughly there, right? It's going to be 3. Use your equation to find the greatest horizontal distance of the bar from O. Okay. Well, we know the the ball has to. What's his name? Find the greatest horizontal distance. So really, it's asking essentially. Well, the ball passes over the bar. So essentially, the ball's gonna have to cross over 3. And if you imagine like a straight line, a line with like this, it's gonna it's gonna be like this. So it's gonna cross the H when H is 3, right? That's this line equation, right? Line is H equals 3. And that's what we're going to do. And it said to find the horizontal distance. So that's x, isn't it? So I think this is essentially solving for x given h. So for part B, we're going to want to substitute h is 3 into equation, right? Into equation. Good job we found it in part B. So we said that 3 now is minus 3 over 100x squared plus 6 over 5x. But this is the quadratic, isn't it? Then we solve it. Uh, the best way is actually to use the, sh- the best way to do this when you solve a quadratic equation with a calculator, right? Just solve it. If you want to show you're working, the best way is to write the quadratic formula and then use the polynomial solver. um, and actually, you get two values here. So x is 20 plus or minus 10 root 3. So that's 37.32 or 2.679 something. And that's in meters, obviously. Okay. So it's 37.3 or 2.67 or 2.7, I guess. Well, it's corresponding to this point here. Oh, this point here and this point here. So that's 2.7 that we found. And the other one was 37.3. So there's two solutions here, but it's asking us to find the greatest horizontal distance of the bar from O. Well, there's two possibilities, so it's going to be this one, isn't it? 37.3 is 20 plus 10 root 3 meters, which equals 37.3 meters to 1 dp. Okay, yep, that's it. Okay. Yes, so that's another thing with modeling questions is with quadratic. Uh, Once you've found the equation, they're going to want you to either find the roots or to find or to solve the quadratic with a given y or h value. So here we are given h value, and we need to solve for x. To solve using quadratic formula. Okay. Anyway, so it says part C gives one limitation on the model, which is quite typical as well. And there are many things you can just memorize. But I think the best one is probably air resistance because it's about mechanics essentially. Its trajectory, it's kicking something, and it's not the path it takes. Uh, but in reality, there's going to be a lot of complex forces acting on it, right? It's a lot of variable forces, and it's not just going to be like a simple x squared, is it? So stuff like air resistance is going to factor in, and actually, also this is displacement or distance, isn't it? Really, if it's a quadratic, it's saying the velocity or the speed, if you differentiate, will be linear, and the acceleration will be constant. As a result, well, it doesn't really make sense for it to be linear, really, or acceleration to be constant. Because, like I said, there's going to be forces acting that will make it a lot more variable. The main force being air resistance. So just think something like that, I guess. But yeah, it's very typical. Sort of so critical model doesn't consider various variable of forces acting. Oh, acting on the ball, such as air resistance. And you can just put air resistance in, I believe. But yeah, that's the sort of method, the sort of thing they're looking for. There is no wind or air resistance on the ball. That's an example. The ground is horizontal. That's a really good point, actually, as well. Because obviously, in real life, the ground is never ever exactly flat, is it? It's going to have like slight edges and bumps and ramps and hills, isn't it? Even though it's very small hilly, very small, it's still going to be a bit rampy, a bit on the field, right? And that obviously will affect it as well. So that's a really good point they made on the mark scheme. The ball needs to be kicked from the ground. Like I said, like again, it's very rare to actually kick it when it's exactly on the ground. Sometimes you accidentally raise it a little bit and then you kick it. The ball is modelled as a particle, so a particle meaning immune to air resistance, essentially. The horizontal bar needs to be modelled as a line. Uh, but it is modelled as a line now, isn't it? Don't know. Apparently that's a criticism now, because that's what we did. We assumed the horizontal bar is a line here. H is free. So I'm not too sure about that. No wind or air resistance. So again, air resistance comes from the wind, pretty much. There's no spin on the ball. That's another one I see common. People love to memorize spin. Say there's no spin when it comes to criticisms. No spin on the ball. I'm not too sure what that means. I'm not the most like mechanicsy person. I assume it's to do with like dimensions and stuff like that, but I don't know. No obstacles in the trajectory. That's a fairly smart point, I guess. Yeah, I guess like if there's like something in the way, then obviously the ball's going to stop midway through, or it will alter its path. You could say that. The trajectory of the ball is a perfect parabola. Personally, I wouldn't give that mark because that's basically not. You want to say the reason why it isn't a perfect parabola, which, for example, is air resistance, but they accept it though. I think they're quite generous with that actually. But yeah, okay. Question 9. Um, oh, we've got a standard first principles question. Okay. We want to use first principles to show that the derivative of cos is minus sine. So, first principles, yeah, you need to know the formula. So, of a function, the derivative is lim as h tends to 0, the limit of f of x plus h minus f of x over h. And that will be in your formula book. Although, if you practice enough questions, it should be in memory. But here it is anyway. It's down here. Okay, I'm not going to go into the derivation of why that is, but they're all the same, aren't they? You keep the limit and you basically substitute x plus h into the function. So I should probably know the function we're working with here. You should probably specify let f of x or f of theta, sorry, be cos x, cos theta, because that's what we're deriving. Therefore, f dash of theta is lim as h tends to 0, and now we just substitute it in. So f of theta plus theta plus h, well, that's just cos theta plus h minus cos theta over h. Okay, now, again, not with brackets. If you have a double angle, it might be best to expand it. So you should know uh, it's in the formula book cos of the double angle. So cos phi a plus b, theta plus h. Substitute that in. So you should know that is cos theta cos h minus sine theta sine h minus cos theta, which comes from here, obviously, over h. Okay. What's the best step now? I think the best step is to put all the cos h's on one side and the on one part, and then the thetas on the other, if we can. Well, no, look, actually, no, look. What are we given here? We're given two things here: sine h and cos h minus 1. Well, where's sine h? Sine h is here, and cos h is here. But sine h is on its own. So it's only sine theta. And cos h minus 1, well, that's in terms of cos theta. So I think it makes the most sense by looking at it is to factorize cos theta and sine theta separately. So cos theta of cos h minus 1 minus sine theta sine h. Okay, and that's over h. And then we can split this up. So lim as h tends to 0 of cos theta splits up into two parts. Cos theta of cos h minus 1 over h minus lim, because it's the same limit. So when you split up two parts, you have to keep it the same. Of sine theta sine h over 0 over h. Cool. Because we're splitting the fraction up into two. Okay. So limits, you can split them up in exactly the same way. Just make sure you include lim on the both of them. Okay, well actually, like I said, we can substitute these values in now, can't we? These tend to, they tend to 1 and tend to 0, and H tends to 0, okay? But H is tending to 0, so we can just substitute these in. So, well actually, the first step we can do is, because cos theta is not in terms of H, because it's only in terms of theta, there's no H involved, we can just bring that out, okay? That will not affect the limit whatsoever. So because H of the limit as H tends to 0 of cos H minus 1 over H, and then likewise it's sine theta is not in terms of H, so we can bring that out. So sine theta of lim as H tends to 0 of sine H over H. And so we can use these rules. So as cos H minus 1 over H tends to 0, that's how to tend to 0, and sine H over H tends to 1 as H tends to 0, which is what this is saying, right? Lim as H tends to 0. So what is happening as H goes to 0? What does this go to? That's all it's saying, and it's saying that this goes to 0 and 1. We can basically substitute this in. So therefore f dash of theta, so our derivative function, wow, that's going to be cos theta um, times 0 minus sine theta times 1 as H tends to 0. That's important here. The only reason we are substituting in is because we're saying H it tends to 0 here. So this tends to 0 and this tends to 1. Okay. So this is important to stipulate here. This does not equal 0 for all values of H. If H is big or whatever, this will not go to 1 and this will not go to 0. It will only happen here when H is 0, tends to 0. This is very, very important to write down here when you're substituting your values in. Okay, that's a very clear point to make there. Now, and then we can just bring this up. So cos theta times 0 is 0, minus sine theta times 1 is simply minus sine theta. Therefore, that's our answer. So the derivative of cos theta is minus sine theta, and that's a standard proof you need to know. Okay. They can ask you to derive from first principles a general polynomial like ax squared bx plus c, or to derive sine theta or cos theta. Okay, but this one they asked for cos theta. Okay, and just a quick explanation. Uh, Usually, vast majority of the time, they do give you this. They'd be very nasty to not give you this, but this comes from, well, this is not right. It's not rigorous, right? There are ways to prove this without small angle or differentiation, but these are true. You can visualize this, but it's not the proof. But you can visualize this is true by using small angles. So you should know that sine h goes to h because h is when h is small. Well, h is small because it's near 0, and that cos h is 1 minus the half theta squared when h is small. Well, sine h over h, that will go to h over h, which will just go to 1. Okay, and cos h minus 1, 1 minus a half theta squared, or half h squared, I should say, because it's not theta, it's h. Actually, let me write that down here. 1 minus a half h squared. Well, 1 minus half h squared minus 1, the ones will cancel out, so you'll be left with minus a half h squared over h, but that will just go to minus a half h, okay? And obviously, as h goes to 0, that will go to 0. Which means this goes to 0. So that's just a quick explanation. There might potentially, they're feeling a bit nasty, ask you to briefly explain why, in terms of small angle, why this is true. But I said, like I said, this is not the proof behind it, but it's just a way you can see why it's the case. Okay, but there are other ways to derive them, but you don't need to know. Okay. Okay, what time is it? 10:47. Might do one more question. Okay, let's end with differential equations. Okay, a spherical mint of radius 5 is placed in the mouth and sucked. Oh boy, God. 4 minutes later, the radius is 3. In a simple model, the rate of decrease rate suggests it's a derivative of decrease is inversely proportional to the square of the radius. Okay, using this model, find an equation linking radius, which is r, and time t. So r has to be a function of t essentially. No, sorry, so r has to be a function of t, okay, in terms of t. And you should define the variables that you use. Well, these are the variables we're going to use. So let r be the radius of the mint and t be the time after the mint is placed in the mouth. Okay. Okay, that's defining the variables. It's quite interesting they ask you to define it here. But yeah, that's what we're working with. You've got to interpret what's going on here. Hopefully that should make sense. Now, equation link. Now, I can spot this is a differential equation because it looks like a question like that. So it's saying the rate of decrease of the radius. So rate of the change of the radius, the rate of change will be dr by dt. Okay. Okay, now it's saying the rate of decrease. Now the decrease just means you have to plug a negative. Okay. If it's an increase, it would just be positive. But obviously that's just the same, right? But if it's decreasing, you have to put a negative here. Okay. So the negative, so the rate of decrease of the radius is inversely proportional then to the square of the radius, which means k over r squared for some constant k. Okay, so k, or otherwise known as the constant proportionality. And you should know from GCSE, I did do a lot of proportion questions on GCSE just recently. Inverse proportion essentially means if y is inversely proportional to x, that's saying y is equivalent to k over x. Okay, so 1 over x times the constant, so it's an inverse, right? And that is because uh, as one variable, and that's what the graph would look like, 1 over x, right? As one variable increases, say as x goes to infinity, y decreases to 0, right? Likewise, as y goes up to infinity, x goes to 0, so x decreases. So as one variable increases, the other decreases, and vice versa. It's inverse proportion, and they're both going to be positive, so you don't have to worry about negatives there. But yeah, that's inverse proportion. You should immediately know that this is inversely proportional. So here, the rate of change is inversely proportional to the square of the radius. So minus k over radius squared, and it's a decrease, so it has to be a negative. Okay. And yeah, all we have to do now is solve. So we need to find the rate r in terms of t. Well, this is dr. This is a differential equation. We have dr in terms of dt, but we need r in terms of t. So we need to solve differential equation, but we also need to find k. But we are given some information. We are given when r is uh, 3, t is 4. And initially, when t is 0, r is 5. Okay, but they don't give us anything about the rate of it, so we can't find k because we can't substitute anything for dr by dt. We only have information for r and t, not the rate of change. So we're going to have to just solve it like this. So this is when you solve a differential equation. So the idea is here to get r in terms of t, get rid of this derivative. You separate the variables, so you put r on one side and dt on the other. So we can times across, so we can say that dr is minus k over r squared dt. And then you get r on this side, so we're going to times by r squared. So you get r squared dr is minus k dt. And that's great news. Now we can just integrate both sides. So the integral of r squared dr is minus k, lots of the integral dt, or 1 dt. You can bring the constant out. Then this means if we integrate a third r cubed, that's the integral of r squared, remember? So the opposite of differentiating, you add the power first and then divide by the new power. So 2 plus 1 is 3, divide by 3. Cool. So then that's minus k, and then the integral of a constant of 1 is just t. So minus k times t. And then there's another constant c. Okay, don't forget your plus c, because they're indefinite integration. So we need a constant. Okay, you got to remember it like indefinite. So you're not sure, so you need to add a constant to make sure. I don't know. Remember how you want, but you need to add a plus c. Okay. Well, actually, now we can bring that information in. So sub r t0. I think let's start with the easy one, right? T0, r is 5. So that means a third of 5 cubed equals c, right? Because t goes to 0. So c then is, if we substitute this in the calculator, uh, gets you 125 over 3. Cool. And then we're going to sub the other condition we're given. So t is 4, r is 3, because that was in the question, remember? That means then a third of 3 cubed is minus k of 4 plus c, which is 125 over 3. And yeah, now we solve the k. So let's simplify it. So a third of 3 cubed, that'd be 9, wouldn't it? Yep, 9 is equal to minus 4k plus 125 over 3. That'll then give you k if you solve that. So 4k is 125 over 3 minus 9. And that'll get you 98 over 3 divided by 4. And k then is 49 over 6. So actually, we can then deduce that a third r cubed is minus 49 over 6t plus 125 over 3. So we have completed it now. We've found all the missing numbers, the constants. But it says r in terms of t. This is not r, this is the third r cubed. So how do we do this? Well, we can times by 3. So just left with r cubed is minus 49 over 2t, because obviously 3 and it cancels with 6. So 3 over 6 is just a half. That's where that comes from. Plus 125. Okay. And then r is the cube root of this whole thing here. Minus 49 over 2t plus 125. Now, this is perfectly fine. Yeah, normally, obviously, you have to be really careful with square root, with rooting. But this is a cube root, so it'll still only give one value for r here. Now, if you're square rooting, that's a no-no because, actually, it might be fine because radius has to be positive, so you'd have to take the positive version. But here it's fine either way because you still get one value. If you cube root, you don't have to worry about plus or minus because that's not what cube rooting is. For example, -1 cubed is -1, but 1 cubed is 1. There's no like plus or minuses, okay? Obviously, but -1 squared would be 1, so that would be tricky. But there's only one definite value for r here, so we can cube root, and so that is our answer here for part A. An equation for r linking t, and that is it. Okay. So then part B says, hence from the total time taken for the mint to completely dissolve. So when the mint completely dissolves, that is when the radius is 0, right? Because there's nothing left for the mint. So part B, mint dissolves when r equals 0. So sub r equals 0 to see what happens. Well, cube root of -49 over 2t. Actually, make that more clearer. Plus, there we go. Plus 125 has to equal 0, right? But we can cube both sides. So we can simply then say that -49 over 2t plus 125 equals 0. Then we can say, therefore, 49 over 2t is 125, which is great because that said time has to be positive. And then, therefore, t times by 2 over 49 gets you 250 over 49, which is 5.1 seconds. No, what is it in? No, it's in minutes, isn't it? I believe it's in minutes. That doesn't make sense. The mint goes away in 5 seconds. I believe it's in minutes. Yeah, it's in minutes. Yeah, it should probably be clear here. The radius in millimeters and the time in minutes should probably be quite specific there. So when you define a variable, also make sure you give the units as well. Okay. It says in minutes and seconds, the nearest second. Okay. So we need to be a bit more careful with this. Yeah, so that's 5.1 minutes. So, okay, the answer is, uh, if I give the full numbers out, uh, that's about 5.102040 minutes. Okay, so it's saying it's 5 minutes, and this is again, I did this in the first. There was a question like this in paper one where it gave you a very awkward answer and asked you to convert it to seconds. So this is the same approach. So we can split this up, saying 5 minutes and 0.102 of a minute. Okay, so this is part of a minute. Okay, but we need to convert this to seconds. Well, we can do that. So we know that 1 minute is 60 seconds. So we're going to times by this. So we're going to times by 0.102 something to give 0.102 something minutes equals well 60 times 0.102. And that's times 60. That is 6.122 seconds. Okay. So this part of a minute is the same as 6.1 seconds. So to the nearest second equals 6 seconds. to nearest second. So to combine that together then, so time is 5 minutes, because obviously this 6 seconds is for this bit here, but we add another 5 minutes on. So 5 minutes and 6 seconds to nearest second. And that is when they ask you to do very awkward stuff like that, when you obviously have a mad decimal and they ask you to convert that to like seconds or whatever, just use this approach, right? Split this up. So split the whole number, so that's into minutes, and then split this decimal up, and then convert the decimal using this into seconds in this approach. That'll work in always the same way, and you should never, hopefully, if you use that approach, um, lose any marks. And bear in mind, to the nearest second is a whole number, so you have to round down to 6. Okay, I'm going to check that's right. Hopefully, I'm not misled anyone there. What's the answer? 5 minutes and 6 seconds. Yes, perfect, perfect. And then what's part C? Is part C another limitation question? Well, it is. Find another limitation to a model. Okay. Well, it does say it's a simple model. But why is that? Uh, well, one way, again, the easiest thing for this sort of question is look at on the model. What it means on the model is essentially the formula, right? This formula here, that is actually a model. What we've done is converted the wordy information into a maths equation. That is modeling, right? This is the model technically. The best way to critique a model for A level notice is think about the large values of t. That will actually go negative, right? You'll get a negative radius, which is not right. And actually, they didn't give us any limitations on our model. Like, it didn't say only consider these values of t. It didn't say anything like that. So actually, it really there's no limits on t. So we can pick any value of t that we want into our model. But that's a flaw because uh, for large values of t, r becomes negative. Uh, but clearly, we cannot have a negative radius. So model is unrealistic for large values of t. And that is quite a common thing to say, right? With models like this. If there's no bounds on, you have to consider probably certain values of t and see if the model makes sense. That's what it's saying there. Does the model make sense for any possible value of t? But actually, it doesn't, because like I said, as t increases here, as you see here, this the t this will go to infinity, but it's minus 49 over 2, so it's negative t pretty much. So negative time, as time is big, that's minus infinity. And actually, if you cube root a minus number, you also get a minus number, right? So r, which is equal to this, will also be negative. Hopefully that makes sense. Okay. Um, okay, I'm going to leave it there. We'll do the next part of the paper next time. But yeah, just as a note, just to go over some examples that's set for that. The model doesn't consider how it sucked. Okay. Doesn't consider whether the mint is bitten, so I guess that splits up the radius right into like because it's like two different spheres, right at that point. So it doesn't consider that. The model is limited for certain time, so t can only be small. So t can only be 5 minutes and 6 seconds, because obviously that's when the radius is 0. When time goes above that, that's when radius is negative. So it could probably be a bit more specific here, but I think you'll be fine. It doesn't say like do not accept like time is large. Like it's fine. This should be fine. It says all equivalent. Like this is equivalent. Yeah, it says not valid for times greater than that. Yeah, that's exactly that. Mint may not retain the shape of the sphere as it's being sucked. But yeah, that's a key point. You're always constantly assuming it will always be a sphere, which is just not realistic, is it? Because that's the whole premise of the model is the fact that it's spherical, that it's modelled as a sphere, right? So that's a really good point there. So again, another point when it says the critique, pay attention to where it said it's assumed or modelled as. It doesn't say assumed, but that's probably a key point here. It says a spherical mint. Um, but yeah, the model indicates the radius of the mint is negative after it dissolves. Uh, yeah, yeah, that's basically what it's saying. So the radius is negative once it dissolves. So when T is large. The model does not consider the temperature in the mouth. Right, yes, I guess you think about like chemistry, I guess, or biology. A higher temperature makes certain actions quicker, right? So it breaks down it much quicker. Model does not consider the rate of saliva production. Uh, so again, like more saliva or variable saliva can break the shape down quicker or slower. Yeah, or the mint could be swallowed before it dissolves in the mouth. Because obviously, some people swallow uh, when there's still a bit of a gum or mint, right, still intact. But yeah, but those are just the examples. But this is a very common one. Like, consider large values of t, and most of the time it should be negative when it shouldn't be. You know what I mean? So that's a very common tactic for those sort of limitation questions. But I'm going to leave that there. Then I'm going to do the next part of the paper next time. But for now, that is it, and hopefully that's helped. Again, any questions, let me know. But I'm going to leave that there then.